Okay, so let's get back to our sessions of this afternoon. And we are very honored to welcome today's session, Professor Karl Friston. And I will just introduce Professor Karl Friston for people who don't know him. And after that, I will give him the floor for his talk. So Professor Karl Friston is a theoretical neuroscientist on brain imaging. Several of his contributions were motivated by schizophrenia research and theoretical studies of value learning. His main contribution to theoretical biology is free energy principle for open systems and its application to action and perception. And also the list is very long, and he received several prizes and honors. He received the first Young Investigators Award in Human Brain Mapping, also the Minerva Golden Brain Award, and he was also elected Fellow of Royal Society and Royal Society of Biology. And also there is very important information for you, dear MoroccoAI community. Friston's papers are cited more than 360,000 citations. So we are in front of one of the great neuroscientists in our time, and we are very honored to have you, Professor Karl Friston. So today, Professor Karl Friston will be talking about deep inference. This is a very important subject, and he will be sharing with us his thought. So, Professor Karl Friston, the floor is yours.
Welcome. Thank you very much for that lovely introduction. It's a great pleasure to be able to talk to you today. I'm going to spend the next 30 minutes giving you a very brief overview of my favorite subject, which is how the brain works. I'm going to do it from the point of view of physics and machine learning, and then return to a more neurobiological neuroscience perspective on the ensuing, what I'm going to be calling self-evidencing. I'm hoping the notion of self-evidencing will become clear. I'm taking a perspective from normative models of how we make sense of the world and how we make decisions, the right kind of choices in terms of what's going to happen next. How that informs artificial research, artificial intelligence research, and then looking at particular biologically plausible schemes or simulating self-evidencing with a special focus on looking for the right kind of information, selecting the data in a smart way. So self-evidencing basically is based upon the notion that we are making sense of the world by making inferences about states of the world beyond our sensory receptors. Crucially, we're going to also invoke inference in terms of inferring what is the most likely thing that I am likely to do next. And we're going to articulate that in terms of beliefs about states of the world and beliefs Q about my actions, my choices, both of which are going to maximize a particular objective function, which is a very generic objective function that I'll unpack in a second, called free energy, and the free energy that I expect if I commit to a particular action or choice U. And I'm going to read this optimization, this maximization of these functionals as perception and action. So just to put a bit of intuition behind that, what is this free energy? Well, effectively, it's a way of measuring the probability of a particular outcome that I would expect given I am me. So these are the outcomes that are characteristic of me, that have value or meaning for me. They define me. And as such, we can read this physics-like formulation of action and perception in terms of choosing things that maximize value. And from that, we can understand things in terms of reinforcement learning, optimal control theory. If I was an economist, it would be expected utility theory. That's nice, because the negative of this way of writing down value in information theory is self-information, or more simply surprise. How unlikely is it that I will encounter this particular outcome given I am me? And that means I can express this formulation of self-evidencing in terms of the principle of maximum mutual information, the minimum redundancy principle, and the free energy principle, where this is the free energy that provides a bound known as an evidence lower bound in machine learning. In turn, the average of this surprise is called entropy. So this description of behavior, sentient behavior, looks as if, or means that, I am going to try and minimize entropy, the dispersion of the outcomes, the uncertainty about the outcomes. And of course, that's the holy grail of self-organization in things like synergetics. But if I was a physiologist, it would simply be a statement of homeostasis. But I want to take another perspective on this quantity. If I was a statistician, I would call this the model evidence, the probability of getting these observations or observed data given me as a model of those outcomes. Strictly speaking, this is a Bayesian model evidence leading to the notion of the Bayesian brain and associated evidence accumulations such as predictive coding schemes. So this is why I'm calling this self-evidencing, because it's simply a description of things that seek evidence for their own models of the world. And I'm going to tell the story in terms of Bayesian belief updating as perceptual inference and active inference as planning as inference. For those of you who like or remember your physics, effectively this is dual to something called the maximum entropy principle. So I've just written out the free energy here in terms of an energy and the entropy here. And the energy is effectively a mixture of the score of the likelihood of my observations, given the states generating, the unknown states generating those observations, and my prior beliefs about the states of the world. And this is exactly dual to or consistent with James's maximum entropy principle from physics. I can rewrite that in another word, that free energy expression in a way that will make sense to people in machine learning, where I can now express the free energy in terms of this quantity here, the log of the evidence, and something that can never be less than zero, called a KL divergence, which just means that I can associate this free energy with the log of the evidence. So as I increase my free energy, I am implicitly increasing a bound on the evidence for my models of the world. And this leads to all sorts of things like explainable artificial intelligence. You can optimize the design of your generative model to make the best kinds of inferences. And as we'll see later, you can also optimize the kind of data that you choose to attend to or to select or sample. This is how a statistician would understand this free energy. I've just rearranged the terms to express it in terms of a mixture of accuracy and complexity. So what that means is that the good models entertained by the brain about the causes of its sensations are that which are as simple as possible, provided they provide an accurate account or explanation for the sensations at hand. And that minimization of complexity is of course, just Occam's principle. It also translates into minimal belief updating, a minimal divergence or movement between my prior beliefs and my posterior beliefs after seeing some outcomes or observations. And that has thermodynamic equivalence in terms of the physics of belief updating and the energy costs of that. So by self-evidencing, I'm effectively inferring and acting upon the world in the most informationally efficient way, but also thermodynamically. So just to summarize that, what we're saying is that to self-evidence, to minimize, to maximize this expected free energy, I'm effectively committing to decisions that give me the best kind of information in terms of the principles of optimal Bayesian experimental design, whilst minimizing the cost or which would be the surprise, or maximizing my value in terms of minimizing the expected complexity. So self-evidencing in the future entails this dual aspect, Bayes optimality, basically getting the right data, but under the constraints that I don't want to be surprised. So just to illustrate that, imagine you're an owl and you're hungry. That basically means that you are, in fact, if I was there, I would now ask you, what would you do? And most people say, oh, I'm going to look for food. And that answer, which is absolutely correct, tells you a lot about the way that you might formulate the describe optimal behavior. So now I'm going to try and motivate this notion of expected free energy as a generic outcome or objective function, and see how it might be calculated and implemented in the brain. But before we do that, let's just consider two different ways that you could formulate optimal behavior in computational neurobiology. So we could start off by saying, there is some value function of states of the world that would ensue if I took this action. And if I knew what this value function was, I could choose the actions that maximize the value for the of any given state, given I'm going to be moving to the next state. So in this formulation, optimal action depends upon states of the world. However, we've just said that the optimal thing to do when I'm hungry is to search for my food. And searching is an act that resolves my uncertainty about where the food is, which tells you immediately we have to have an objective function, not about states of the world, but about the beliefs about states of the world that include uncertainty. So this is the self-evidencing perspective, where we don't have a value function of states, but what we have is something called a function of a function of beliefs about states that would ensue if I committed to this action. Furthermore, it matters the order in which I do things. So if I try to eat my food and then search for it, I get a very, very different outcome than if I first search for my food and then eat it. And that ordering means we have to consider sequences of actions, sometimes called policies. And I've just written that down mathematically here in terms of finding the right policy or sequence of actions that maximizes the integral, or the sum over time, sometimes called a path integral, of this expected free energy. And you will come across many of these, or many examples of these two approaches to describing optimal behavior. These commitments to optimal action depending upon states of the world, sometimes described in terms of Bellman's optimality principle, would include optimal control theory, dynamic programming, deep reinforcement learning, Bayesian decision theory, and so on. This is an alternative approach. It's much more belief-based and much more about rolling out into the future and planning explicitly. And this would include things like active inference, artificial curiosity, and intrinsic motivation in robotics, optimal design, sequential policy optimization, and so on. So just to give you a feel for the complementary ways in which you can start to formalize or naturalize in physics optimal behavior. In fact, what we'll see is one is a special case of the other if we do certain things. If you don't like maths, don't worry about these equations. I've just written them out in full just to highlight a particular symmetry, which I think is quite compelling, between the free energy in the moment, this score of value or negative surprise, and what I expect if I commit to a particular policy, in this instance, pi. So I've just written the free energy out here in terms of the statistician's version, in terms of complexity and accuracy, and in terms of the machine learning version, in terms of a log evidence and a KL divergence that makes it into an evidence band. So what about the future, though? Well, outcomes in the future are now unknown. There are now random variables that are not directly observed. So what I have to do is to take an average of this free energy under what I expect to see, observe, if I committed to a particular policy. And what happens is that the complexity becomes risk, the accuracy becomes ambiguity, and these two terms become expected information gain and expected cost, respectively. And just to put, again, some intuition on this, let's just ignore the expected cost for the moment and just ask, what is this expected information gain? Well, in neurobiology, and certainly in the visual search literature, this is known as Bayesian surprise. It's basically a measure of how much uncertainty I have resolved in terms of the difference between my beliefs about states of the world, given what I would see if I did that, relative to my beliefs at the moment in the absence of those observations. So it scores the information gain. It's also simply the mutual information, the information gain between the causes, like states of the world, and the consequences, the outcomes in the future if I do pi or I commit to this particular policy. And that's why it's called expected information gain. Let's just take some special cases. Let's remove ambiguity. So I can see everything. If I know the states of, if I see my observations, I effectively know the states of the world. So there's a direct mapping between the two. So now my states become observations, and I'm just left with this risk. So what is this risk? Well, it's just the difference between what I anticipate will happen if I do this, and what a priori I think will happen to something like me. And in engineering, this is known as KL control. In economics, is known as risk-sensitive control, basically measuring the divergence from your prior preferences. Let's take a final move and take all uncertainty off the table. And ask, what do we get? Well, we're just left with the expected cost, which we said at the beginning is just the expected value. So now we've come back to a Bellman optimality principle simply by removing uncertainty, where we can now read the expected free energy as underwriting things like expected utility theory in economics. So to summarize, maximizing expected free energy is effectively just to maximize the expected value, given I'm also maximizing the information gain or resolving my uncertainty or expected surprise about the world. And the last couple of minutes, I just want to give you now a more neurobiological example of this kind of mechanics, this kind of self-evidencing in implementation, in simulation. To simulate this kind of behavior, we usually use something called a probabilistic graphical model or a generative model that can generate causes from consequences from causes. We sometimes write it down as something called a factor graph, just to look at the mechanics of the message passing. And I've just described the mathematical form of these models here. Again, we don't have to really worry about their particular how they relate to the optimization. It's standard off-the-shelf equations and updates. The interesting thing is that they look very, very much like the things that go on in our brain. So remember, it's all about inference. It's all about trying to infer the states of the world causing my sensations. So what don't I know? Well, I don't know the states of the world, and I don't know what I'm doing. I don't know at the moment, before I've done it, what I'm going to do. And also, I don't know the confidence that I ascribe or the precision that I ascribe to what I'm going to do. So there are only sort of three kinds of things that I have to infer. And if I just write down the free energy maximizing updates, given some observation here, what we get is an update, a Bayesian belief update, that has a functional form that looks very much like how we understand neuronal message passing and neuronal dynamics in the brain. Effectively, it's a sort of nonlinear function, like a voltage current relation, a sigmoid function of linear mixtures of observations and representations or expectations about the past and the future. Policy selection is just a simple softmax function of our expected free energy, the goodness of a particular policy. You will find in conventional economics. and the precision looks very much like a reward prediction error that you'll find in the literature on dopamine. Learning, if we apply the same principles to the parameters of our generative model, in this instance, the initial states of the world as they start, say, in a trial and experimental task, it has exactly the functional form of associative plasticity or Hebbian learning with associative and decay terms here. And then, as we just said, we can now select the action from the inferred policies that I am most likely to commit to, just given these updates here. And you can play all sorts of interesting games about where in the brain these different processes might be evinced. And I put a rough cartoon here with the visual information coming into the occipital cortex, state representations in the hippocampus being evaluated in terms of the best kind of policy in the prefrontal cortex, evaluating the precision of that in the basal ganglia, and then generating an action or selecting an action from my beliefs about what I'm going to do next. So let me conclude with a very simple example. This example is as simple as possible, but tries to illustrate this information gathering aspect of self-evidencing. And what we've done here is created a generative model where there's a little mouse and it can make 2 moves. And its objective is to, or what it values, is being with its food or reward, the red ball here. But it doesn't know whether the red ball is on the left or the right-hand side. However, it can go down and use its first move to go to the lower arm and get an instructional cue that will tell it whether it's on the left or the right. Now, from the point of view of reinforcement learning and expected utility theory, it can either take a chance and go to the right or the left arms, and I should say it has to stay in the arm it chooses, and therefore can spend 50% of its time with the reward twice, or 50% of its time with the reward no time. Or it can use the first move to find out where the reward is and then go and secure the reward. So again, 50% getting the reward. So from the point of view of the expected utility, both of these choices are the same. But from the point of view of self-evidencing, clearly going to the bottom arm to get the instruction clue to resolve uncertainty about where the food is the optimal behavior. And we can simulate that. And here's an example of a simulated simulation of this kind of exploration and exploitation. What we've done here is simulated 32 trials, and under the initially by switching the position of the reward, but then we played a trick on the synthetic mouse. We left the reward on the left-hand side. And what happens is, as time goes on, the mouse realizes that the reward is always in the same place. So that means that there's less information gain or less epistemic affordance for going down to the bottom arm, and it can get more reward, maximize its expected value by going straight to where it thinks the reward is as it becomes familiar with this particular consistent environment. And we can see that with a transition in terms of beliefs about the best policy at trial 20 here, where there's a jump from this kind of behavior to going straight to the reward, as learning the context it means it's more and more confident and there's less and less uncertainty to resolve. So this is basically making quite a fundamental point that when we enter a new situation, the information gain is going to be much bigger than the expected value or the exploitative aspect, which means that the information gain, the resolution of uncertainty, the epistemic affordance, the exploration will dominate my behavior. But as I become more familiar with my environment, then at some point that expected information gain is going to fall below the expected value, and I'm going to switch to becoming exploitative, and my behavior will be then determined by the expected value. And that's exactly what happens here. And we can play all sorts of interesting games. One interesting thing we can do with these simulations is to compare the responses to various cues before and after the agent and the mouse in this instance has become confident about the environment. So the cues have different meanings for the mouse. And if one does that, one can do all sorts of interesting analyses of the simulated neuronal responses using those belief updating equations that I showed you earlier on. We can simulate the evolution of responses during the trial in terms of the chosen and unchosen options, as often done in small animal and non-human primate electrophysiology. We can plot the responses of various expectations or beliefs or representations of these beliefs as a function of where the mouse is, and what emerges is place cell-like activity. And we can even do mismatch negativity studies and the like. But what I'm going to finish with now is a different kind of epistemic foraging. So here is our generative model, here's our factor graph. And what I'm going to do now is put one of these generative models on top of another generative model in order to induce a separation of temporal scales, to induce a depth of a temporal sort to my generative model. So machine learning, these would be literally deep models because they have this hierarchical depth. And I'm going to use exactly the same maths and simulation setup to simulate an agent who has to now do an elemental form of reading. Instead of reading letters, they're going to read these iconic letters here that can be composed in specific ways to mean different words. For example, flee, feed, and wait here, using this Markov decision process generative model, where states generate outcomes through some likelihood, and the transitions that are controlled are denoted by these B's here. To make things interesting, though, I'm going to now have a second level that has a model of what words should follow each other to compose sentences. So this synthetic agent believes that there are 6 kinds of sentences that she might be reading, and has to now choose when to look from one word to the next word. But within each word, she also has to choose at the lowest level which letter to look at to resolve uncertainty about which sentence she is reading. And we can simulate this kind of deep epistemic foraging and reproduce eye movements in terms of where the agent is looking as she's reading a sentence. And this is basically a result of that simulation here, where this is the word that's being, the sentence that's actually being read, composed of the iconic letters here. This kind of simulation evinces exactly what you and I do when we read. We sort of skip over the uninformative stimuli and choose to look at those parts of the sensorium, in this case the visual scene, that will resolve the greatest uncertainty about what is causing my sensations, both in terms of the word I'm reading, but also the sentences that determine what is the most likely word. For example, she knows immediately that this has to be a flea because the only word with flea in it is a cat. So she jumps straight away to the next word. It's a bit confused because there's nothing here. It's a bit ambiguous, but on the second move means it must be a wait. I won't go through the details here. So jumps to the second, the third word. So I'm showing you exactly the same results here, but just to illustrate the separation of temporal scales in terms of this kind of belief updating of a biomimetic or biometric sort at the 2 levels of this deep model. So this is basically showing how evidence is accumulated through this belief updating slowly about one or more of the 6 sentences. And this level shows the belief updating and the switching of beliefs or expectations about which particular word is currently being examined. And you can see immediately that the words change as we do the reading, do our epistemic foraging, and slowly accumulate beliefs about the word until only at the very last stage can we disambiguate between the first and the fourth sentence, which is discriminated in terms of the last word, which is wait versus flee. And here are the simulated electrophysiological responses, just to make the point that they are remarkably similar to the kind of empirical electrophysiological responses that one sees in the literature, here illustrated in terms of pre-saccadic delay period activity in the prefrontal cortex, which are likely now to sort of spiking activity in these populations encoding particular beliefs about, in this instance, the sentence. In terms of electrophysiology, here are some results from monkey electrophysiology at a higher level and a lower level due to perisaccadic activation or field potentials during active vision. Look very, very similar to the kind of responses that we are simulating. So I'll finish there and give Helmholtz the last word. I should note that much of the intuition behind the physics of self-evidencing comes from the work of Helmholtz, particularly his work on unconscious inference, and of course his introduction of the notion of free energy. So each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, it only remains for me to thank those people whose ideas I've been talking about, and of course, to thank you for your attention. Thank you very much indeed.
Thank you so much, Professor Karl Friston, for this incredible talk. And what attracts me most is the formulation of neuroscience field with mathematical equations. And I think that every person was interested in his childhood by interested in the comprehension of the human brain and also the functions of the human brain. So my question to you, Professor Friston, with the AI system that we are building now, because there are relations between AI and also human intelligence and artificial intelligence and neuroscience, do you think that the AI system that we are building now, based mainly on artificial neural networks, are the best way to build a strong, let's say, digital intelligence? Or do we need other theories from neuroscience in order to build stronger systems?
That's an excellent question, of course, very relevant in terms of current investment in many senses in large language models and transformer architectures in technology. I think the answer to that, I think most people in the know would say that we absolutely need neuroscience and bio-inspired biomimetic principles. And certainly, if you believe that the current hype cycle with generative AI and large language models is currently peaking, that's where people are now looking. And by people, I mean some of the good and great who are actually involved in building generative AI, for example, Benjo and Lacan are both in their own way promoting the importance of the first principle accounts that speak to natural intelligence. So as you say, what people are really interested in is the way that you and I work, natural intelligence. So how do you make artificial intelligence more like natural intelligence? Then I think you have to put the principles behind natural intelligence and self-organization, and I would argue self-evidencing, into artificial intelligence. And that will, I think, mean a change of direction. So, for example, large language models, or certainly transformer architectures, generative AI, as we currently know it, do not have a sense of agency. And in fact, they don't even have agency. They cannot decide what data they're going to train on. So they're just given everything and hope that something comes out which is useful. Natural intelligence, or certainly active inference of the kind that we've been talking about here, actually decides what is the most useful data I can go and train on in order to resolve my uncertainty. So I think one fundamental change in the direction of travel, which is towards a more neuroscientific perspective, is to put proper agency into these models, which means equipping them with generative models of the consequences of their action so they do things. And I think that's a bright line between current artificial intelligence research and what people aspire to, which sometimes is summarized under AGI, or artificial general intelligence.
Yes, and in addition to neuroscience and the human brain, another mystery, I think that the two most important mysteries in science are the comprehension of the human brain and the understanding of the universe. So if we take a look at the universe in physics, we can notice, Professor Friston, that there are some theoretical foundations. There are some equations, something related to strong mathematical theories. And what we have seen during your talk, Professor Friston, that there are also equations in neuroscience, but could you just compare between these two fields? Or can I ask this question, is the comprehension of the human brain is harder than the comprehension of the universe itself?
That's an excellent question. From my point of view, no. I think you're absolutely right. I think the game would be to use those equations and dynamics, the calculus that describes the universe in terms of physics, and then apply them to try and understand the brain as a very, very special kind of self-organizing system. And there are some unique features of things like you and me that, say, insects or thermostats or viruses may not possess, but we all should be described in terms of these fundamental laws of physics. So, I referred to two of them in my talk. One of them was the free energy principle, which starts with so in the classical version, which just starts from something called a Langevin equation, from which you can derive classical mechanics, statistical mechanics, and quantum mechanics. So it has the same inheritance, has the same foundation as physics. James's maximum caliber, or max-cal, or maximum entropy principle, is another example of this. Feynman's pathological formulation, when applied to a system that is separated from the external world, can also get you to this kind of description. So I think your question probably is, well, my answer to your question is absolutely. You should be applying first principles, usually in terms of probability density dynamics, from physics to neurobiology. The question now is, in the application, what are the special challenges that present themselves when it comes to things that understand and things that make sense? And I think, actually, interestingly, the big question, or the big challenge here, is exactly the same answer as the previous one. It's agency. The fact that you know that you are an agent, and you have a generative model of the consequences of your actions. You know what you will do, and as soon as you have that kind of aspect to your generative models, that's private to you, because it's the consequences of your action. And furthermore, as I was trying to demonstrate in the presentations, those actions depend upon what you believe. So it's not just physics now, it's actually the physics of belief, of belief updating. But it's still just probabilistic physics. It's still just exactly the same kind of physics you find in quantum theory, but raises some deep questions about what it is to understand, what it is to forage for the right kind of data. And the free energy principle is one attempt to draw the links between physics and belief updating, which is, provides an elemental kind of sentience. But I do repeat, agency is so important here. And of course, you could argue, do I know I'm an agent? Well, possibly not everything does, but you and I do. So that puts another layer, a deeper layer on the generative model.
Mm. And regarding the free energy principle, there is a question from the audience. So they say the free energy principle assumes prior knowledge of the space of possible states and its structure. How can a model leverage the free energy principle to discover the structure?
Excellent question. So that's a field some people call structure learning. If you're a statistician, it would be called Bayesian model selection. And I use those two phrases because in the work of people like Josh Tenenbaum, for example, which can be characterized as something called radical constructivism, then they address the problem of how to find the right structure, the right number of levels, for example, in a deep model, the right number of states. I would read that as a free energy optimizing process, because Bayesian model selection is just selecting the right structure that has the greatest evidence, Bayesian model evidence. So if you apply the free energy principle now to the very structure of the models, you get structure learning. Interestingly, the phrase Bayesian model selection is also informative because it suggests, as many people currently believe, that natural selection is nature's way of doing Bayesian model selection. So they don't come from nowhere. All of these free energy optimizing processes are nested within other free energy optimizing processes at different scales. So we didn't discuss this in the presentation because we didn't have time, but one is assuming that the models have been optimized at a slow timescale through a process of Bayesian model selection. It could be natural selection, but it doesn't have to be over evolutionary time. It could be the kind of natural selection that we get when we're growing up, say during neurodevelopment, and we're selecting, do we keep this connection or this particular projection, or do we prune it? And that's sometimes cast in terms of Bayesian model reduction.
Okay, thank you so much. I have also so many other questions, but maybe I will finish with the final word, maybe Professor Karl Friston, to our MoroccoAI community and also our young researchers.
Right. So I wasn't expecting that, but my final word is, first of all, thank you for inviting me to talk to you. It's always, I think, very compelling when young people ask older people. And one piece of advice is effectively inherits from that formalism that I just described, which is keep your options open and realize that to be is to be curious in the sense of exploring, responding to epistemic affordances. And in a sense, that's exactly what everybody's doing now. They're spending their time gathering information for their models of their lived worlds.
Thank you so much, Professor Karl Friston, for accepting our invitation, and hopefully will be with us during the next edition in person here in Morocco, and share your thought and insight with our MoroccoAI community. Thank you so much, Professor Friston.
Thank you. Bye-bye.
Bye-bye. If we can just get back to the backstage.